I assume you are okay. Then let's move to another topic, right? So SRAM, to be frank, I'm not expert in SRAM. I cannot tell you too much, although I do some research on SRAM on the radiation hardness. We do have some paper on that, but SRAM is really important. Let me make a joke about my friend again, right? So I went to PhD in, I got in between 2001 and 2006. I have a friend, he's from India. His RAM is SRAM, and then he has been doing SRAM since in his PhD degree. And then after he graduated, he went to AMD, still SRAM, right? So SRAM is so important. It actually spent here, 20 years, right? It's just doing SRAM. So he buy his house using SRAM. He get married because of SRAM, right? Because all the money, right? Or kids or whatever, right? So we actually don't call him SRAM. We call him SRAM because it sounds like SRAM, right? So SRAM is really important. So this one, just telling you that in terms of layout, you need to pay attention. It's a little bit old technology, right? But the main point is that, like what we said before, the bit 9, the word 9, we try to use the metal one. Remember that if you use poly, it's going to take a very long line, right? So the delay is proportional to L squared, right? And it's proportional to L squared, and then so it is very slow. So that's why we use some resistive, low resistive metal to do this wiring or to reduce the delay, right? So this is they usually use metal 1. And also you see that in the past it might save more area if you have some corner. Look at all these well or implants. You have a lot of corner, right? Like here Q5 like this. But nowadays we try to make it very regular. In particular, if you look at the FinFET one, right? I don't have this for you, but we did this study also because for FinFET you need to actually do very regular patterning. So these are the so-called fin. So what we did is this. We actually put the poly gate here. So here you have a transistor. For example, this is the pull-down transistor. This is the gate, right? On top, I have the pull-up transistor. This is not pull-up. This is the SS transistor, right? This is the gate, right? Now, didn't I tell you that we want to have a stronger pull-up than the SS? But in this FinFET layout, they have the same size. What should we do, right? So in some cases, right, not exactly, but some cases, what we do is we just actually don't use this gate. We just don't use this transistor, but we still pattern it. The fin is still there. So as a result, I have twice the driving power at the pull down than the SS transistor. But I still need to print it. I cannot just say that, oh, since I don't need this one, let me print it in this way. No, then you cannot do it because now we are printing some very dense pattern. I think I mentioned before, right? So you need some very regular pattern. Try to refer to lecture 3 or something. I talk about the modern technology, right? So in the future, if you have chance to do the layout, try to see this. You will find something very strange. Why we are wasting doing something that doesn't make sense. So even you see in sub 90 nanometer, they already think that we need to have very regular well, okay, active, right? So let's take a look. For example, this one is word 9, right? So this is the SS transistor, right? Because this is the word 9, it goes into here, and then the other side go to the bit 9, right? And then this bit 9 will go to here, and here you see I have a pull down network because the drain, the source is connected to the ground, and then we have this pull up network. Not pull up, I just pull down and pull up, right? Pull down transistor and pull up transistor, right? And they share the same gate. This is the gate. This is the gate, right? And their drain have the same output because they will then connect to the other pair. This is the gate of another pair, Q2 and Q3. And what you are seeing here is just a rotational symmetry. You rotate this whole part by how many degree? 180 degree, right? Then you will get this part. Now, why they want to do this? Remember, we want to have a very regular structure. We have many rows and columns. By doing this, you see that I can drop the word line vertically, right? But then I'm going to have a line that running horizontally. And then for this bit 9, where's the bit 9? Bit 9 and bit 9 bar, right? I can drop it vertically so that every cell will share the same bit 9, right? I go up and down, right? And then this ground and VDD, of course, we need to also connect them. Again, you need to use higher metal layer to connect. Okay, so that is a typical SRAM layouts, but SRAM is really a very important and difficult thing. I cannot give more comments, right? But do you have any questions? Okay, so now you know how to read, you know how to write, and you know how to do layout, right? Of course, we did not go into detail, but you see, okay, yeah, we do layout, make it regular, so I can instantiate them, and so I do a 1000 by 1000 array, then I get an SRAM, right? But how do I read it? Now, you already know this is the SRAM cell. Do you see that? Right, this is SRAM cell. And then you need to imagine, right? I'm going to copy this laterally to many columns, vertically with many rows, right? But for each column, I have a bit 9 bar and bit 9, right? Just like here. For each column, I have a bit 9 running vertically because this go to maybe M1, right? Metal 1. And then I need to think of a way, if there's no other metal, if there's metal connect to metal 2, and then I run vertically, right? It does, although it's inside the SRAM, but doesn't matter. It's just saying that we are schematically, it's just like outside, right? It doesn't matter. We have many bit 9. So, and then we adjust it vertically, right? So how do we read it? We already stated to read it. I just pre-charge this to VDD, right? And once I pre-charge this to VDD, I turn on the word line. Once I turn on the word line, it's going to discharge me, right? For other column, word line is 0. They are not going to discharge it. And then we go to a sense amplifier to amplify it. Okay, so let's see how it works. So first of all, we will have something called EQ, equalizer. The point is that we want to make sure the left and right are at the same voltage, because the way we sense the signal is by comparing the bit 9 bar and bit 9 voltage. So if they start differently, then it will give me a signal already, even I have not read it, right? So that's why the first thing I try to pre-charge it, turn on this equalizer. Once this turn on, then they have exactly the same VDD, just in case there's any leakage. Okay, so I pre-charge it. This is the pre-charge. Then we turn on the word line signal. So this is turned on, right? So we start reading during this time, right? After that, we will stop. This one will stop because we turn off the transistor. So you see that this period is kind of your SRAM reading speed. And how fast you can read is 1 over this period will be the frequency that you can read, right? They were talking about. And then, of course, you can do a lot of parallel operation. And then they tell you what is the reading speed, like how many gigahertz, how many megahertz, how many megabits of data per second, right? So once I turn on, then if you remember, this was at 0, this was at 1, right? Then I will start discharging. I'm going to discharge the bit 9 bar, okay, gradually. But the bit 9 won't change because this is 1, right? So eventually, there will be a tiny difference, we don't want to wait until the whole thing is discharged. Why? Because this is a very long line, a very large capacitance. To fully discharge it can take very long time. So we only let it discharge a little bit, okay? And then when we think that it is enough, right? We designed it before. We turn on this sense amplifier enable, turn this on. Once this is turned on, if any of you have taken analog circuit, you know this is just a single-ended differential pair. Okay, this one turn on basically just as a current source, right? Then it compare, right? It will compare the value, they amplify it, and then it will come up with the output, whether it's 0 or 1, right? So here I got very confused at the beginning, but basically this graph is saying you either get this waveform or this waveform. Okay, you only have one. Okay, so that's the procedure of doing this sense amplifier. So understand this, then you will start appreciate how you should decide the discharge time, right? Because the capacitance is very large. Do not think that you can make this large. And then now you go back to the sizing. Remember we say, let's try to make this minimum. If this is minimum, then this has the weakest ability to discharge it. So SRAM is going to be slow, but your SRAM cell is going to be small because now if you increase the width here, the cell is going to increase, right? So you need to think about all of these things, okay? Any questions? If no, then there's another scheme, right, which can be faster, also less power consumption. Is instead of using the latch, right? So instead of using the sense amplifier, it use the latch. The problem here is this: if you look at the sense amplifier, this has a impedance equals to infinity, right? Because they are connected to the gate. But for latch, this is just a couple pair. You actually, this is just like this, right? Basically, this one is just like this, like an bistable as latch, right? You are connected to here, so that this one is not infinity. So that will be a problem. So as a result, so we need a must. We need this to cut it off when we are not using, right? So that is how it does, right? So at the beginning, we need to pre-charge the line here. We just pre-charge everything. We pre-charge from here, okay? Instead from the top, only pre-charge here. And then you turn on the word line, okay? Once you turn on the word line, then you are going to discharge the bit 9 and bit 9 bar, right? So once you discharge to a certain amount, what we're going to do is then now I turn on this enable and also turn on the must. So when you are done, you turn this on. So this one won't touch this one until you think that you are ready. And then it will amplify. And this one is faster, just to show you that this is another possible scheme. And the biggest difference is that we have a must here to disconnect the bit 9 because the impedance is not 0. If you don't connect it, then you might have problem when you operate, okay? Okay, any questions? If no, then let me see, right? So we have a different figures of merits for the sense amplifier gain. Why gain is important? So you can detect the signal with small discharge, right? So it means even a little bit difference between the bit 9 bar and bit 9, right? I can detect it. So it means it can be very fast, okay? But so you also want to know what is the minimum detectable signal, right? This is also the same, right? Is that 1 millivolt, 10 millivolt, or whatever? Right? But you also need to be careful about the common signal, right? There's maybe an offset. So your sense amplifier can also amplify the common mode, right? I don't know if all of you remember what it is, but if you have learned earlier, for example, for a single-ended differential pair, right, like this V in minus, V in plus, right? It has two gain. One is the differential mode gain, ADM, right? It's talking about the V out as a function of the delta V in, right? Differential mode, right? It only has gain if there's a difference, right? For example, if I, let's say V in plus and V in minus, if they are 5 volts, 5 volts, 5 volts, right? And then let's say if, for example, this is 100, then the V out equals to 100 times 5 minus 5 equals to 0, because there's no difference. That is our purpose, right? We want to see difference between the bit 9 and bit 9 bar, right? This is bit 9 bar, this is bit 9, right? And maybe your bit 9 is the same, but bit 9 bar becomes 4.99 volt. Then this becomes 100 times 5 minus 4.99. Then it becomes how much, right? It becomes 1 volt, a very big amplification. And that is what we want. Once you have 10 millivolt difference, I amplify to 1 volt. I know, oh, the data stored there is 1 or 0. This is the differential mode gain. Right. But unfortunately, because of the non-ideality in the op-amp, we are not going to derive here. It also has something called common mode gain. And it is common mode to differential mode conversion ratio. It's talking about what is the V out. If I have a V in common mode change. For example, it can be 1, right? For example. So what does it mean? For example, well, V in plus and V in minus, either you have 5 volts, right? And the common mode, then it means its common mode is 5 volts. Then your V out is going to be 1. Oh, that is ugly. Let's say 1E minus 3, right? E minus 3 times 5. And this will give you what? 0.005 volt output. Okay. So that is the problem. For example, if this dropped to 4 volts, right? Then this one will be 0.004 volt, right? Then that will be a problem, right? Because we don't want the fluctuation of the bit 9 and bit 9 bar to affect our detection. So ideally, I only want to see the difference, not the absolute value, right? So that's why we also have something called common mode rejection ratio. It's talking about the ratio between the differential mode gain divided by the common mode to differential mode conversion. We want it to be very large. Okay, just know that you have this one. Rise time, fall times are also important because they are related to how fast you can amplify. Okay, so the sense delay is what? Your output reach 50% of the value you want, minus the time your word 9 reach 50%. Why? Because we start reading when we turn on the word 9. So it is at this point. Okay, and then you reach 50% of the output here, right? So this is the, if you keep going, right? This difference is the, what do you call? Sense delay. So sense delay is another component that make your SRAM smaller, right? Before that, we also have this other charging, other operation, but sense delay is one thing very important. Okay, any questions? Okay, so we talk about sense amplifier. I hope you have picture now, right? We start with the SRAM, simple SRAM cell. We know how to read and write. You know that pull down has to be stronger than SS, stronger than pull up. And then, right, we can lay out, and you see that we can arrange them in a line and column. And then now you see that for the whole column, we did not show every row. What we need to do is do the right timing. Turn on the word line, pre-charge first, turn on the word line, and then let the sense amplifier to amplify. There are many engineering problems, including how can we make it sensitive, but at the same time, we need to be immune to noise, right? And also how to, and then how to measure the delay due to sense amplifier. Okay, so good. So now we know how to read in the whole column, okay? But how do we write it? We also know how to write, but we need to drive it, right? Yeah. So to write it, this is important. Remember, our purpose is to discharge one of the bit 9 very quickly. Remember, look at this one. How do we write it? Look at this one again. Our goal is to discharge this one, right? This was at VDD. I don't care about the other one. I want to discharge it so it reach the VTH of the Q1. Then the whole cell will flip. Okay, so this is our goal. So how do we do it? That is, we have many logic that can be used, and it is very easy, right? Just look at one of them. Let's just, for example, I say write enable. WE means write enable, right? For example, if I want to write 1, then I say, no, I mean, I want to write it, I say write enable. For example, I want to write 1, right? Then this is 1. So what will happen? This becomes 0. If this is 0, this is on, right? And then, of course, then this is off, because this is write enable bar is 1, and then write enable is 0. So this transmission gate is off. This is 0, right? And this is 1, right? So then I will be able to make bit 9 bar equal to 0 to discharge. I don't care about this bit 9 actually. And actually, if it is floating, that is the best. Because if you look at this, not the best, it doesn't help much, right? Then look at this, yeah, even this is floating. The point is I want to make a 0 here. I want to tie the bit 9 to 0. Tie one of the 9 to 0, right? So bit 9 here, I want to write the right one, right? So here, because I want to write 1, so bit 9 bar has to be 0. Okay, then I can write it. Just imagine this is a whole column of the row. Okay, I mean, similarly, if you want to write, let's say you say I want to write 0, then this one will becomes 1. Okay, and this one will become 0. Okay. Now, how about this one? If we make this 1, then this will turn on, this will turn on, right? If I want to write 1 here, then this becomes 0, and this is 1. So this is off, this is on, right? So the whole thing, am I right? 1, 0, 1, right? Then the whole thing will be pulled down to 0. Okay, and then we are able to flip it. Right? It's similar here. If this is 1, this is 0, right? Because this is 1, then this is 1, this is 0, right? Then this will be 0, right? But this is 1, so this will be 1. So this will turn on, and then this one will write 0. Okay, so these are the writer driver, right? So we need to make it to be 0 to write it. Any questions? Now, if no, then the next thing is how do you do the decoding, right? So we know how to write it, how to drive it, but now I need to select the correct word line and bit line, right? I need to make the correct word line on. So now the question is, I go back to here, which word line will receive this signal to turn on, right? So we need to do decoding, right? So there are many ways we can code it. We come up with an address, right? This one is NOR gate with a static PMOS loading. It saves area because you just all you need to do, right, for different word line. For this one, word line 0, if I have all of this 1, 1, 1, then it will give this one 0, right? Because it pulled down. And if this one is 0, then of course it's not going to turn on. Right. So it depends on this what you put in, and then the corresponding row will turn on. Okay. Another thing, what you can do is do the dynamic logic, right? You pre-charge it and then you try to discharge, right? But these are not that good. They save a lot of area, right? Another thing we can do is a multi-stage decoding. As an example, let's say if your address is A0, A1, A2, A3 equals to 0, 1, 1, 1. Then what happened? Then it means your bar A0 and A2 and A3 are 1, right? So this is 1, this is 1, this is 0, this is 0. We use LAN gate. So you see that this 2 will be 1, only this is 1. All others are 0. Right, this is 0 because A2, A3 are 1. So any of them have negation becomes 0. How about A0 and A1? A0 is 0. So A0 bar is 1. So this is 1, this is 0. So as a result, you get this one equal to 1 because this is activated. Okay, so this is the first stage. Right? After this, we go to the second stage. We know this is 1. Also, this is 1, right? But we connect it accordingly. As you can see, this will be 1, and this will be 1. So then we successfully select this line, which is the word line, connected to 0, 1, 1, 1. Okay, so there's different decoding scheme. Any questions? Right. So, but you know, not just this, we can also, because the SRAM can be very huge, so we can have different block. We have different block. So if you give me an address, right? For example, you give an address, this I make a simple one, only 0, 1, 0, 1, 0, 1. Let's say you have 6 bits. So we have a global decoder. So for example, this 0, 1, let me make 1, 1, 1, then you will be very clear. This I come with 0, 1. Okay, this is the global decoder. So only one of them will turn on. For example, this turn on, this turn off. No. So sorry, I say the wrong thing. What I'm trying to say is you have a block selector, right? Sorry, let me say it again. This one is the block selector. For example, this is 0, 0. This is 0, 1. This is 1, 0. You have different blocks. So maybe this one is turned on. Okay. And then you have a global detector. This might be 1, 1, 1, 1. Then all of that get at 1, 1, 1, 1. Right. But only this is for the row, for this row. Right. Then only this 9, this is on. Right. This is also on. But this is off. So then you were able to select this block. And then you use the word line to select the row, and then the bit line to select the column. Right? So this is a way to do this decoding. I might be too fast. Any questions? The bottom is just similar. It's just that we go to another level of hierarchy. Right? You have more bits, then I just go to another level. Any questions? Can you hear me? I keep talking. Should I move forward? Okay, let me move forward, right? Now, we also have a column decoder. Column decoder is what? We need to select which pair of bit 9 to decode and then put into the sense amplifier, right? We cannot have sense amplifier for individual column because sense amplifier is large. And also at the same time, we need to select which column to use. Okay, now, so here we have a 2 to 4 decoder. So what does it do? What it does is, this is A0 bar, A1 bar. When it is 0, 0, it get activated, right? But maybe yeah. And this is for A 0, A1, right? And then this may be A0, A1 bar. And then this is A0, A1, right? So depends on the input, they will be activated accordingly. And these are all connected to the sense amplifier. Okay, so what is the problem of this one? You see that if I have a K bit, K is the number of bits, I need to have a very complicated multiplexer, right? So I need to have a very complicated decoder. But however, the rest are good. On the other hand, I can select it in a 3 decoder action, right? So what it does is, if this is A1 is equal to 0, then these are all on. Okay, and these are off. So I select half of them. Then depends of A0. If A0 is 1, then this is 0, then these are off. Right? And this is on. So as a result, column 2 gets selected. And the problem of this is that you have a stack of transistors. And how much is that? It is the log 2 of K. I mean, or K, just K, right? How many bits actually? How many bits? K is talking about the bits. So you have 2 bits, you're stacking 2 transistors. If you have 8 bits, that's too much. You're stacking 8. Remember all the delay that we discussed before, right? So that can be a problem. Okay, is that clear? As you guys, anyway, yeah, just stop me if you have question. I don't know. It's very difficult to teach online, and I don't want to probe you because you might be busy with something else. Any question, let me know. Finally, it's about the timing, right? We know how to do row decoding. We know how to do block decoding. We know how to do the column decoding. We know how to read, how to write. We know how to do layout. We are done. The problem is how we're going to control the SRAM. Okay, so what we can do is have a finite state machine, and this machine can have some delay in between. So after a few timing option, right, certain time, then you trigger another option. And what I'm trying to say is this one. Address, when are you going to send the address? When are you going to pre-charge the bit 9? When are you going to enable the decoder or activate the sense amplifier? Right? If you forgot, look at this graph again. This is a pretty complicated timing diagram. I need to do the pre-charge, turn on word 9, and then wait, and then do the sense amplifier and must, and then detect the signal in the right time, at the right time, right? So that is the what we need to do, right? But the problem is this: when you fabricate your device, you really don't know what the delay is going to be. By the way, we don't want to have a complicated logic to sense it because it makes your SRAM very slow, right? So we use some delay elements to finish this certain delay, and then you send out the pre-charge certain delay, you enable the word line, and then you activate the sense amplifier after certain delay. But the delay can change when we do the fabrication. So People are very smart. We did similar thing before. Remember how we dynamically change the frequency of the CPU by the OS? We have a replica of the circuit. So what they are doing here is I have a dummy column of SRAM. This guy is not used for real storage. It is used to detect when you finish the sensing and when you finish the amplification, right? And based on this, once we find that it finished, then we can call the logic to do the real thing, right? So there will be a difference between the timing because the dummy is very different the real SRAM, right? The time when you do the differential output will be the CV over I. This is the time, right? The read current, right? Divide the capacitance, and then for the voltage difference, this is the time for reading. How do I know that the reading is completed? I don't know. I really don't know. But I can have a dummy one, also have the time for reading, right? And I want to make their time the same, right? Equal the time, equate the time, right? Because if this row is done, then this row is done also, right? So I try to equate them. Then you find that all I need to do is just make my dummy current proportional to this factor, to the read current, right? For example, if the dummy voltage, what I'm looking for is only 0.5 VDD, half of the VDD, right? And then the difference I need in the reading for real SRAM is 0.1 VDD. All I need to do is just to set my dummy current equal to 5 times of the read current. So then by doing this, I will know that whether my dummy is ready, then I can just send the next signal to perform the operation. Okay, I think I overrun 4:16 already. Let's stop here. Any questions?